This lecture is part of a series of lectures on error formulas when using numerical integration techniques to estimate a definite integral. These numerical integration techniques fall under the class of techniques called the Newton-Cotes techniques. For this series of lectures, we tackle the trapezoidal rule, the midpoint rule, and Simpson's one-third rule, or plainly Simpson's rule. For this specific lecture, we tackle Simpson's one-third rule or Simpson's rule. We will subdivide the lecture for the derivation of the error formula for Simpson's rule into two parts. This lecture will be part 1. We mentioned that these numerical integration techniques can be used to estimate the definite integral of a function f over an interval from a to b. If the function f is continuous and non-negative, then this definite integral can be interpreted as representing the area between the graph of f and the interval ab on the x-axis. Whether or not the definite integral represents the area underneath the graph of f, in order to use Simpson's rule, we subdivide the interval from a to b into n subintervals. For this lecture, we use a uniform partition, that is, the subintervals are all of the same length. Designating h to be the length of each subinterval, h will be equal to b minus a all over n. With x equals a being the first partition point, we set a to be equal to x sub 0. Then we simply add the subinterval length h to each partition point to get the next partition point. Simpson's rule requires that the number of subintervals be even. We are using n equals 4 subintervals for the illustration, so that b equals x sub 4. On the graph of f, we take 3 consecutive points at a time and fit a Lagrange polynomial through the 3 points. Because we are fitting a Lagrange polynomial through 3 points, the degree of this polynomial will be at most 2, so the Lagrange polynomial will be either linear or quadratic. Examining the 3 points at x sub 0, x sub 1, and x sub 2, because the 3 points are obviously non-collinear, the Lagrange polynomial will be quadratic, whose graph will be that of a parabola. Observe that we are also taking 2 intervals at a time. This is the reason why Simpson's rule requires that there be an even number of subintervals. Taking the next 2 subintervals, or the points at x sub 2, x sub 3, and x sub 4, we fit another Lagrange polynomial, and with the 3 points being non-collinear, the graph of the polynomial should be that of another parabola. To derive the error formula for the estimate, we focus our calculations on just the first 2 subintervals. Then, using the error formula for the first 2 subintervals, we make a generalization to cover the entire interval from a to b. At this point, we use a couple of ideas to simplify our derivation. The first idea is to use a translation of the graph along the x-axis. Translations in any direction, and not just along the x-axis, belong to a class of transformations of the plane called Euclidean isometries. Euclidean isometries are special in a way because they preserve distances and angles, and by extension, they preserve areas. And as a further extension, every translation along the x-axis preserves the values of definite integrals. The values we get out of Simpson's rule are also not affected by translations along the x-axis, because after all, the formula for Simpson's rule can be obtained using the definite integral of the quadratic Lagrange polynomial through points on the graph of a function. For the translation, we take the point at x equals x sub 1 and translate it to x equals 0, so that now the y-axis is at x equals x sub 1. X equals x sub 2 is h units to the right of x equals x sub 1, and so x sub 2 will be translated to the point at x equals h. The point at x equals a is h units to the left of x equals x sub 1, and so this point is translated to the point at x equals minus h. So the Lagrange polynomial capital L of x will now be through the following points: minus h y sub 0, 0 y sub 1, and h y sub 2. The next thing that we will do is to break down our function f of x into its odd and even components. We write down f of x in the following way. It is easy to check that f of x is equal to the sum of the following two terms. The first term is half of the quantity f of x minus f of minus x. And the second term is half of the quantity f of x plus f of minus x. Observe that if we replace x by minus x in the first quantity, we end up with the negative of the quantity, so that the first part is the odd part or odd component of f of x. And if we replace x by minus x in the second quantity, we obtain exactly the same quantity. The terms might have been switched around. So the second quantity must be the even part of f. Now, what is the significance of this fact? Take an odd function capital M of x equals y, such as the sine function or y equals x. Then integrate over minus h to h. It is a well-known fact that the value is equal to 0. So if we integrate a general function f of x from minus h to h, the odd part will produce a value of 0 for the integral. So only the even part can possibly contribute something non-zero to the integral of f. Now, what about Simpson's rule? How does the odd part of a function affect the Simpson's rule formula? Let us take another look at our odd function capital M. Estimating the integral of capital M from minus h to h using Simpson's rule. This is approximately equal to h over 3 times m evaluated at minus h plus 4 times m of 0 and plus m of h. Now remember that capital M is supposed to be an odd function, and so capital M of minus h is equal to minus capital M of h. So the first and the third terms in the Simpson's rule estimate for the integral of capital M of x from minus h to h cancel out. In addition, if m is odd, then m of 0 is equal to 0. This means that the odd part of any function has 0 contribution not just to the definite integral of the function from minus h to h, but also to the Simpson's rule estimate. And so without loss of generality, we can assume f to be an even function. If the function f is to be even, then it has to be symmetric with respect to the y-axis, so that the y values at the two endpoints should be equal. So now assuming that f is even, we fit a Lagrange polynomial through the 3 points at x equals minus h, x equals 0, and x equals h. It turns out that the quadratic Lagrange polynomial through the 3 points ends up being an even function as well. That is the linear term. The term with x to the first power is not present in the formulation. And so we should be able to find two constants, capital A and capital B, so that capital L of x is equal to a times x squared plus b. It is a simple exercise to show that L of x is equal to x squared times the fraction y sub 0 minus y sub 1 all over h squared plus y sub 1 times h squared. This concludes part 1 of this two-part lecture.